Here are some practice problems for the kinematic equations. If you feel like you know the answer, go ahead and pause the video, solve it yourself, and then see if we get the same thing. A penny's dropped down a well. How fast is it going after 5 seconds? This is the simplest of the kinematic equations, which is given here. The key word here is dropped, so we know that the initial velocity is 0. We define down as the negative direction, and we assume we're on Earth, so we have an acceleration of minus 9.81 meters per second. And if we plug that into the calculator, we have our final velocity of minus 49.1 seconds. I'm using 1 decimal point. How far did the object in the previous problem travel? For this one's the second of the simplest kinematic equations. And we use this formula. Again, it was dropped, so we have an initial velocity of 0, and if we define the top of the well as x equals 0, and the guy drops it down here, then our initial position is 0. Our final velocity is going to be this, 0.5 times minus 9.81 times 25 seconds squared. This will give us a distance traveled of 122.6 meters. A guy throws a rock down a cliff with an initial velocity of 2 meters per second. How fast is it going when it hits the bottom? For here, notice that time isn't given to us anywhere in the problem statement, and there's only one kinematic equation where time is not included in the formula, and that's this guy. It's important to note here that d doesn't denote the distance traveled, it denotes the displacement, and that'll become evident in the next problem. So our final velocity is the unknown. Our initial velocity is a negative 2 meters per second if we define down in the negative direction. Acceleration is also in the negative direction. And here, displacement is again in the negative direction, negative 10 meters if we define the base of the cliff as 0 and positive in the x direction, x equals positive. And so we have our final velocity squared equals 200.2 meters squared per second square. If we take the square root of that, we have plus or minus our final velocity equals plus or minus 14.1 meters per second. And we know it's minus because it's going in the negative direction. This is a similar problem, and we use the same kinematic equation. This is just to emphasize that here we're dealing with displacement, not distance traveled. So our initial velocity here is positive. It's in the positive direction, but again, our displacement is in the negative direction, as well as is our acceleration. So here we have 25, which is 5 squared, plus 2 times minus 9.81 times a minus 10, and all that together is going to equal 221.2 meters squared per second squared, which gives our final velocity, if we take the square root of both sides, as 14.9 meters per second. So why does a positive velocity, a velocity in the positive direction, why does that contribute to our final velocity in the negative direction? And think about it like this. If he throws it up at 5 meters per second here at x equals 0, how fast is it going on its way down? Because of conservation of energy, it's going at minus 5 meters per second. So it doesn't matter if you throw it up at a certain speed, it'll be coming down at the same speed. So it doesn't matter whether this term is negative or positive, it's still going to contribute to the final velocity as long as we keep all our signs correct. And that's a common error in a lot of physics students have, is just making sure that acceleration has the correct sign, displacement, as well as velocities. As long as the signs are consistent, this equation works. A train has an initial velocity of 5 meters per second and accelerates to 20 meters per second in a period of 20 seconds. Its initial position on the tracks is minus 100. What is its final position? Here, we are going to use this kinematic equation. Oops, I can't write. V initial plus V final over 2 times time plus our initial position. And all we have to do here is plug in the appropriate values. Your initial velocity is 20 plus 25 divided by 2 times our time period of 20 seconds plus our initial position of minus 100 meters. Gives our final position of 30 divided by 20 seconds divided by 2 times 20 seconds minus 100 gives a value of 200 meters down the track. So that is to say, if we start here at minus 100, we're going to end up over here at 200 if we keep on accelerating this way. A penny's dropped down a 30-foot well. How fast is it going to reach the bottom? This is the exact same as the first problems, except this is imperial units. Final velocity equals minus 32.2 feet per second squared. Oh, this is not the same as the first problem. This is, again, it doesn't have time. So final velocity squared equals, it is dropped initial velocity squared, which is 0, plus 2 times acceleration minus 32.2 feet per second squared times distance displaced, which is a minus 30 feet. And we can solve this. To get a final velocity squared value of 1932 feet squared per second squared, or the final velocity equaling 44.0 feet per second. A rocket accelerates at a constant rate of 30 meters per second squared for 10 seconds and has an initial velocity of 20 seconds. How fast is it going after 10 seconds? So it's accelerating at a constant rate and it has an initial velocity. We want to know the final velocity. Left with, we have 30 meters per second per 10 second, and we have to add on that initial velocity. And this is the first kinematic equation we used. Gives us 320 meters per second as our final velocity. A particle accelerates at 20 meters per second squared and is measured to have an initial velocity of 300 meters per second and an initial position of 20 meters. Where is it after 3 seconds? And this is the second kinematic equation we derived. 1/2 times 20 squared times 20 times time squared, which is 3 squared. Everything here is in the positive direction, and it has an initial position of 20 meters. So if we solve this, 0.5 times 20 times 9 plus 300 times 3 plus 20 is going to give us a final position of 1,010 meters. This is the final problem in our set. A parachutist falls with an initial velocity of 10 meters per second and a final velocity of 59.05 meters per second after 5 seconds. How far down did she fall during this time period? So we have initial velocity and final velocity, but time isn't given in the problem statement. So if we take final velocity to be 59.05, we square that, and that equals the initial velocity squared plus 2, and we assume that this is on Earth. Both of these should be negative because she's falling in the negative y direction, times minus 9.81 times d. And we can go ahead and solve for d in this case by subtracting out. The signs are going to end up positive anyway. Subtract this term and divide by 2 times minus 9.81. And that'll be our final value for distance. And so we have a value of 172.6 meters. And if you look at this problem, another way you could have solved it is she is falling with an initial velocity of 10 meters per second, and she falls for 5 seconds. You know what time was given to us in the problem statement. So this is one way you could have solved it. You have initial velocity and final velocity, so you can use this kinematic equation, or you can solve it by calculating it with this guy right here, 1/2 times 5 squared plus the initial velocity, which is a minus 10 meters per second times 5 seconds, and the initial position is 0. So if we calculate this, again, we come up with 172.6 meters. So there was a lot of information given in this problem, so you could have solved this multiple ways. Great, I hope you enjoyed the video, and if you have any questions, leave them in the comment. Thanks for watching.